Hello. So I think we will just wait 4 more minutes for everyone to have the chance to join, and then we start. All right. So I think we gave everyone the chance to join now 5 minutes. So we can begin. Yeah. Hello, everyone. Welcome to this webinar about enhancing industrial automation by integrating mobile robotic applications into IEC 64099. Yeah, thank you for attending this webinar. It's a pleasure having you here. And please note that this session is going to be recorded and made publicly available later. I am Fabian Thiele from Fraunhofer IPK. That's a research institute in Berlin, Germany. And with me is Dr. Pujan Safari from Fraunhofer HHI, also in Berlin. Then Shreya Desmukh from Next Control. and Dr. Said Adil Abbas Kasmi from Opticoms. We are part of a consortium and working together in the Zero Swarm project, which is an European research project that focuses on accelerating advanced technologies like 5G, digital twins, cloud edge computing in the European manufacturing sector. One part of the project is merging different products and technologies that are developed individually into an applicable use case, which is called a trial. And in the trial we are working on, this is about mobile robotic systems, 5G process control with IEC 61499 and the bridge to ROS2. And these are also the topics for this webinar. So why is this interesting? We will go into more details about the IEC 61499 standard later, but on one hand, this IEC 61499 has its own range of benefits like modularity, portability, and reusability, and is also easily integrated into PLCs in production processes. On the other hand, we have robotic applications, which most of the time cannot directly be controlled by a PLC because the robot manufacturers provide interfaces, for example, in ROS, robot operating systems, which cannot be directly accessed from a PLC, but you may be able to build the connection between them. And yeah, such interfaces like the robot operating systems are really important in robotic processes because they help to accelerate the development process, and many functionalities are only available in these frameworks. So the problem really is how to bring these two together while keeping both of their benefits. And that is what we will talk about today. So this brings us here to our agenda for today, where we begin with the more general topics and go into the specifics later. We start with the ROS2 framework for robotic applications and the IEC 61499 standard. So the big two environments we use here. And then we explain our ROS2 IEC 61499 interface we developed to help these two environments to communicate with each other. And on point 4, we go into the demonstration, our trial of a mobile robotic applications, where we start with a general overview of the use case we implement here at Fraunhofer IPK. Then we go over the autonomous mobile robot, our edge cloud, 5G network and communications, and last, the process control using IEC 61499. The last point is a quick summary, and then we go over to the Q&A part of this webinar. The total duration will be about 45 minutes, where we use 35 minutes for the presentation and about 10 minutes for questions and discussion. So we planned a whole hour. We now started 5 minutes later, but should be all in time. Okay, so we can begin with the ROS2 framework for robotic applications. So the Robot Operating System 2, ROS2, is an open source framework for robotics, which is quite broadly used in the robotics community. It is first emerged in research, but is now more and more used in practical applications in the industry because it really suits this task for robotic development. Like there's no real alternative, and there are on one hand use cases for ROS in manufacturing, like we do here, but it also is used, for example, for cleaning robots. And even NASA deploys it for robotics in space. And yeah, it's basically everywhere where we are working with robots. So this framework, ROS2, includes the modularization and communications concept. It has libraries for frequent robotic functionalities, such as path planning, for example, or transformations of coordinate systems, mapping, so creating maps of the environment and so on. And it also contains a lot of tools, for example, for simulation, visualization, what you see here on the right, and debugging of the applications which are implemented in ROS. It is also an own packet management and build system. And this whole framework combined really enables the fast and efficient development of robotic applications. So despite its name, robot operating system, it's not really an operating system, but operates on top of, for example, Ubuntu, most of the cases. And when I'm now talking about ROS in this seminar, I talk about ROS2, which is a new development or redevelopment of ROS1, where a lot of improvements are implemented that couldn't be really added to the first version. So they created instead of updating it, they created a new ROS2 framework. And this mainly includes better support of, for example, multi-robot systems, real-time support, and really focuses on giving features that make it easier to integrate the ROS solutions into practical real-world applications. So it's not only be primarily used in research. So one key concept you need to understand for ROS is that it has a specific computational graph or communications architecture where a ROS system consists of multiple nodes, which you see here in this graphic, these three different nodes, which all every node has a specific modular purpose. For example, one node could be controlling wheel motors of a robot, or another node can be responsible for publishing sensor data from a laser range finder, for example. And these different nodes communicate with each other using topics. And this is this graph you see here on the bottom half. For a topic, you always have a publisher and one or more subscribers. And on one topic, the publisher will publish a message, which, for example, could be the charge of a battery of the robot. And then we have different subscribing nodes. When they are interested, they subscribe to their topic. And this could be an HMI, human machine interface, which displays the current charge of the robot to the workers. Or another node could be maybe some managing node, which will detect when the battery charge drops below, for example, 5%, then the robot will do some driving to a recharging station or something like that. So on one public, there's always one type of message, a publisher and one or multiple subscribers. But this is not only robotic internal messaging. You can also give commands to the robot via topics. For example, you could publish a specific pose or position on your shop floor in the factory, and then subscribers to this topic may use this pose, which is published, to drive to the specific location. There are actually a few more concepts or means of communications in ROS systems, such as services, which you see here on the top, or actions, but they all are based on topics or on this quite simple concept of a topic, and expands it a little bit. But these services and actions are not really important now for the context of this webinar and our application. Yeah, so this is really the key point you may take away from this ROS communication architecture. We have these different nodes with specific purposes, and they communicate with each other using topics. And now I will hand over to Shreya, who will tell you about the IEC 61499 standard for distributed automation.
Thanks, Fabian. I would like to start with the basic definition of what is IEC 61499 in case we have some new people. So IEC 61499 is a standard-based system-level design language for the distributed measurements and control systems. The key component of this language is a basic function block, which we can see here, an event-driven function block. It is a self-contained software component. That means we can design the behavior of this function block using the ECC. ECC is a control chart which has a state machines, so it can be defined when an event comes and the data is available at the data input. At a particular state, an event is triggered and the particular functionality will be executed within the event-driven function block. The next is, can you please click on the screen? Yeah. The next is application model. The application model is nothing but the network of different function blocks, which an application we can design to create an operation, or we can have an application model creating different type of processes. The last key component is, can you please click? Yes. System model. System model gives an user an advantage of distributing its application, which is independent of the hardware, to the different devices. Together, these key components, IEC 61499 makes a technology enabler. Can you please go to the next slide? Okay. A little bit about event-driven function block. The first picture you see, this is a basic function block. As I said, it's a self-contained software component provided the function through the defined interface. So you see data inputs and event inputs, where an example is given a motor. A behavior of a motor can be designed in this basic function block using different languages. For example, structured text. If I want to deploy the application to the PLC, I'm using structured text to define a behavior of a motor. And with the help of execution control chart, I'm going to trigger the behavior using different data inputs. The most advantageous thing of basic function block is you can test it real time and right time. So anytime a behavior stops, you can debug this function block at any time in any operation. The second category of a function block is a composite. As the name said, it is a composition of different function blocks. Service function blocks, a CAT function block, or it's a combination of different types of operations together. The last category comes, it's service function block. The service function blocks comes into the picture when we have inputs and outputs of a device hardware which we want to access. So IEC 61499 gives us an opportunity to access the I/O systems, or the input outputs, or the services provided by different hardware to access within IEC 61499 environment. Together with the help of these function blocks, we can create our application, which will be independent of any hardware. Please, next slide. Yes. The second layer is application model. Regardless of any hardware we have, we can create our application. A user gets an advantage of create an application, define its behavior, and where this application will run will be defined by the user. Can you please click on the slide? Yes. As the picture says, regardless of any hardware, we can design our application and we can deploy this application to several distributed control nodes. In the traditional way, the application was completely dedicated to one device and it was restricted towards deployment of the one device. In IEC 61499, since we have a flexible architecture, we can switch from centralized to distributed node. So the application do not have to be particularly running on one PLC or one control node. It can be on several devices can be used. These devices can be actuators, motors, can be PLCs, can be edge computers as well. Please, next slide. So the last is system model. System model gives us opportunity to map the different function blocks we create, different application we create using 1499 function blocks to the different resources or different devices. A system model maps the hardware to maps the function blocks to hardware on which the application will execute. And since it is an event-driven structure which allows automatic establishment of communication paths across the network. When you click on the slide, you will see, yes, an application is created, it is mapped to two different devices, and the automatic cross communication will be generated within IEC 61499 environment. Next slide, please. Well, the first 3 slides were the basic key components of 1499. With the help of these function blocks, service function blocks, you can create an application. A user can define an application which has different behaviors, but I would like to focus on one of the key advantages of 1499 environment, which is the IT-OT convergence. I am very happy to say that IEC 61499 gives an automation engineer or a simple user an opportunity to create one object which can have OT, which is the interface to the shop floor, which can be PLCs, as Fabian says, which can be data coming from the PLCs or the sensors, and this data can be communicated with the help of IT. That means well-known and accepted IT protocols, which are now industry-driven. We can use them in IEC 61499. We can create one object, and we can use this object more frequently in our application and have this OT to IT communication. One of the few well-known, can you please click on the screen? As I said, one object designs and defines an interface to the IT, and the same object can be used in an application to have the communication or to use the IT communication protocols, for example, 1M2M or MQTT protocol to publish and subscribe the data from a broker, which can be used by the user by defining and designing only one function block. This gives an automation engineer or a simple user an opportunity to play with user-oriented or object-oriented devices. A real device can be defined or designed using 1499 as a function block or a composite automation type, which is also a type of function block. And this function block is reusable and multiple type in a multiple way in a system IEC 61499 environment. So with this slide, I would like to conclude the IEC 61499 part and would like to give the mic to my colleagues. Thank you, Fabian.
Yeah. Thank you, Shreya. Now that we went through the benefits and the basic functionalities of on the one hand ROS2 and on the other hand IEC 61499, I want to show you what we developed, which is our ROS2 IEC 61499 interface, which helps them communicate with each other and keep benefits from using both environments. So here we used for that TCP/IP communication because it is on one hand supported by IEC 61499, and on the other hand ROS2 can make use of basically any C++ or Python library. So of course TCP sockets are also supported. Here we have a diagram on how this interface works. On the right side, we have this IEC 61499 side. Here it's labeled as EcoStructure Automation Expert, which is the development environment of Schneider Electric for IEC 61499. And on the left side, we have our ROS2 side. When we want to publish from the 61499 side, we first need to generate a message we want to publish. We also need to know on which ROS topic we want to publish. And then this message is encoded using this encoder entity, which basically generates a byte stream with a byte stream which can be put into TCP packages which are sent to the ROS sites via network. Here this byte stream is received and decoded on a ROS2 proxy node. So this ROS2 node has a modular purpose of communicating with IEC 61499. And it can, on one hand, receive, decode, and then publish on the actual ROS2 topic, but it can also subscribe to ROS2 topics and forward this subscription to the 614.99 site, where basically the same process is happening. So we have, again, we have this data we want to forward, and this will be, again, encoded using the same encoding technique as here on the other side, then sent via TCP/IP, received using this NetIO function block in EcoStructure, which supports this network TCP protocols. And then here it will be decoded and made available to the program logic. So you can see that basically both parts, decoding, encoding, sending, receiving, are implemented on both sides, and they are just on the other side of this interface block are made available either as data connections for the programmable logic or actual publishing on ROS2 topics and subscribing on ROS2 topics. So the important part of this is this generator node, which means all the code, all the function blocks for this interface can be automatically generated. So the user just has to define which ROS2 topics to actually publish on and subscribe to. And all the ROS2 code for this proxy node, and also the function blocks for 614.99 are generated automatically. On the next slide here, you can see how such a function block can look like. So this is, of course, depending on how many ROS2 topics are supported. On the left side, you have here these topics, for example, AMR status or AMR move, which are where you can publish on. And on the right side, you have topics with event outputs and data outputs, where this interface block is subscribed to. So on the bottom side, you can see how this composite function block is looking inside. But for the end user, this really has, there's no use for them, because all of this will be generated, as I said, automatically, and the user can just import this function block, drag and drop it into this graphical programming environment, and use it there in 614.99. All right, so this brings us now to our actual use case, this demonstration of a mobile robotic application. First, I will give you a quick overview of this use case we implemented here at Fraunhofer IPK. And we have, in this use case, 3 different shop floor devices. First, we have this mobile robotic arm. Then we have an intelligent storage rack, and we have an assembly station. And what is happening is that we are depicting a part of an assembly process of a fuel cell, where we have some bipolar plates stored in a cassette. Well, there are 4 different plates for this fuel cell stored in the storage rack. And the AMR will then first get asked if it's available using such a get status message, and then drive to the storage rack, where it is checked if there are, first of all, any parts available, and then also where in the storage rack the parts we need are stored. So the storage rack has different positions where the part could be. Then the robotic, the mobile robot will pick and place the part onto the robot, then drive to the assembly station, also do a pick and place action there. So place the part in the assembly station, and then the assembly station will be triggered also using in this scheduling to start the assembly process. And this is really the process we want to show in our use case. All the steps are coordinated and scheduled in 61499 running on a Schneider Modicon M262 PLC. But the low-level actions, for example, the path planning, controlling of wheel motors on the AMR and such things are still implemented in ROS on the device itself. And to go to our mobile robot, to give you a bit more insights there. We are using here an in-house development, but this robot uses commercially available parts, components. For example, this Near 100 robotic base, which is the actual mobile robot. Then we have here some electronics, charging equipment in this middle part, and we have the UR5 collaborative robotic arm on top. This is an robotic arm certified for human-robot interaction, and also commercially available. Then this robotic arm has an RGB depth camera mounted on at the top at the tool center point, and also has different interchangeable fingers for the parallel gripper. So here in the bottom right, you see here we have very small, these orange fingers to grab this item profile, but we also have different fingers which are interchangeable to suit the actual task. So all the algorithms for the robot are programmed in ROS2. And also the interface for external access on robot functionalities is also written in ROS2. So you can use specific services or publish on specific topics to actually make the robot move somewhere, move the arm, and so on. This robot has, because it's wireless communication, because it needs to drive all around in the shop floor, and there it has access to Wi-Fi and 5G networking. One special feature is that all the low-level operations, so for example, as I said, like controlling the wheel motors to move somewhere, are implemented on the computer on this robot, but more computationally intensive calculations will be done on an edge cloud. So we have this edge cloud, which Pujan will soon talk about at Fraunhofer HHI, where via wireless communications we can do things like path planning or image processing. So when the robot sees something, it will just send the video or image data via network to this edge cloud, where then we have a lot of processors, a lot more RAM to process all these actions needed for calculation. And this is what Dr. Pujan Zafari from Fraunhofer HHI will now explain to you, and also he will give some insights into our network setup used in the trial.
Thank you, Fabian. Hello and good afternoon. And sorry for my voice, I'm a bit sick. I will briefly introduce the Edge Cloud as one of our necessary infrastructure for our trial. This is Fraunhofer Edge Cloud, or FEC in short, and it's a blueprint of a Fraunhofer initiative to create an edge cloud environment for research, development, test, and demonstration of various use cases and applications. This is the envision map of the connectivity between different nodes within Germany. And the current FEC instances that we have running at HHI comes with GPU acceleration and TSN compatible network interfaces. They can be used for distributed computing and provide virtual services and real-time processing, as we will see in our trial. Data sovereignty, such as GAIA-X, IDS, and medical data space compliance are at the core of this FEC concepts, and they can be used for interinstitutional projects such as the one that we have in Zero Swarm between HHI and IPK, and they can be used for higher TRLs to establish, for example, spin-offs and commercialization purposes. Next, please. So these are two different sites, Fraunhofer IPK as the production site or hardware layer, and Fraunhofer HHI as the edge cloud provider site or service layer. They are physically apart in Berlin, and you can see their location pointed out on the map, and together they form a kind of 5G networking of the factory shop floor as an enabler for industrial use case demonstrations and field trials. Also to integrate AGV into 5G network and perform control of AGV via edge cloud services. Next, please. So this is a simple schematic of the connectivity between HHI and IPK sites via 100G city deployed fiber. I don't go into any detail, just to know that the FEC instance is located at the HHI, and you can create different virtual machines to perform, for example, different control services and 5G core on the FEC instances. Of course, FEC is behind a firewall, and there are multiple switches and routers involved to provide the connectivity. On the IPK side, we have basically the 5G antennas and some other necessary infrastructure to provide the connectivity together with the 5G core at the FEC to provide the 5G networks, basically. By this, I would hand over to the other partner to talk about the 5G itself. Thank you.
Sure. Thank you, Boyan. So I would like to elaborate a little bit on why are we incorporating, or let's say, why have we selected 5G technology as the connectivity solution for our trial. And I would do so by mentioning that 5G provides the performance, reliability, and quality of service that is, needed to, let's say, automate and digitalize the manufacturing facilities and automation, which is basically required in our trial. So in this slide, I tried to come up with the features, the services that are offered by 5G. Some of which are, let's say, better coverage. So 5G provides better coverage as compared to other connectivity technologies. With 5G, we can go up to, let's say, 200 meters or above coverage area in comparison to other 3GPP and non-3GPP technologies, where the coverage area is relatively less. And in a scenario like our trial, where we have, this production area, large production area, or a factory or a manufacturing facility where this geographical area is large, this continuous wireless connectivity, this wireless coverage becomes important. And so 5G provides it. 5G provides better coverage as compared to the other technologies. I would not like to go in a lot of technical details, but I would like to very briefly describe that 3GPP has been introducing and proposing in their releases for 5G, some enhancements, some new dedicated protocols and procedures to improve all these capabilities of 5G. For, let's say, to achieve the better coverage in 5G, they have introduced some concepts like, let's say, small cells in 5G, to MIMO, to proposing some enhancements in 5G optimization techniques, etc. Similarly, 5G technology provides better, or let's say high precision positioning capability. With 5G, we can get an accuracy of several meters, or we can even go up to an accuracy of 1 meter. And with regards to positioning capabilities, we have, there are several non-3GPP technology positioning technologies like radar-based positioning capability, LiDAR, and even Wi-Fi signal strength-based technologies. But every technology has its own limitation. 3GPP and 5G specifically complements and incorporates all these technologies to achieve better positioning capabilities, or let's say to offer better positioning solutions. They're also coming up with enhanced new protocols. Let's say one of the protocol that I could remember is called NR protocol, positioning protocol A, for to enhance this positioning capability, let's say. But I would like to mention one thing, that the selection of software and hardware components for the 5G network, let's say for the 5G core and the 5G RAN, is very important to have the appropriate, or let's say to have the right capabilities, right functions and features in place. Another important feature of 5G that we are using and that we are exploiting is its better handover capability. So this is one of the distinguishing features of 5G. Basically, this seamless user and control plane data continuity without any interruption in mobility scenarios, be it an indoor, let's say, mobility scenario or an outdoor mobility scenario. And the mobility interruption time, and sometimes we call it handover interruption time, is between 30 to 100 milliseconds in 5G. And 3GPP has been introducing new protocols to even minimize this handover interruption time further. For example, there is this protocol called conditional handover protocol, or this dual active protocol stack. And the idea is to allow the 5G capable devices, this AMR or AGV in our trial, to have this continuous data continuity, to allow reliable communications and to have as minimum as possible this handover interruption time. Then we have other features of 5G, like enhanced mobile broadband, and this feature basically allows to achieve higher data rates. In our trial, recently we are achieving up to 100 Mbps, which is appropriate, which basically allows, let's say, the video data to the edge cloud, where it is evaluated on this high performance computing hardware. Then we have ultra reliability and low latency communications, the service by 5G. So we are achieving latencies between, let's say, as minimum as 10 milliseconds to up to 20 milliseconds. And with obviously reliable communications and with low latency values, we can control this mobile manipulator or this roboting arm even in real time. Massive machine type communications is another important feature of 5G, which supports massive number of IoT devices and this low power, less complex sensors. So cutting the discussion short, in summary, we are incorporating 5G technology as the connectivity solution to exploit the features of 5G, like its better positioning capability, better handover capabilities, low latencies, reliability, better coverage area, to basically support some of the features in our trial, like environmental perception of, let's say, the shop floor at Fraunhofer, because this AMR is interacting with its environment at Fraunhofer, to support features like self-positioning, self-guiding of the AMR, because our AMR or our robotic arm is able to take decisions based on the data we are collecting through the 5G network. So yeah, so this is all from my side. Thank you so much for listening, and over to you, Fabian.
Okay, thank you very much. So now you got an overview about the general use case we implement here. You got information on the mobile robot and the special setup with an edge cloud and our 5G communications used in the trial. So now the last part really is the implementation of the scheduling and the control of the whole process using IEC 64099. And for this, I prepared this diagram here on the right side, which is a very simplified version of what we use in our use case, but it is easier to understand in this simplified version. So the core part really is this ROS2 IEC 64099 interface, which I presented earlier. And this is communicating with our shop floor devices. In this case, here it is just the AMR for this example, but in the real use case, we also have this SMT station and we have the storage rack. So these shop floor devices are here in the green part. And on the other hand, we have this scheduling here on the left side, where we have one functionality of a ROS2 device is always one function block here in IEC 61499. So for example, one functionality would be this AMR move to function. And we have this function block here, which can be triggered to activate, in this case from the start block. But it also gets input data because the AMR can obviously move to lots of different positions. And these positions or general configuration data are stored in this configuration data block. And for this function block, there would be this position 1, which could be the position for the storage rack provided to this function block, which then communicates via this ROS2 IEC 64099 interface with the AMR. And what is really happening is that there is a topic the AMR is listening to, this AMR move to topic, which will be published here from this block using this path. And then the AMR drives to the storage rack, for example. And when one operation is done, another operation is triggered, which can also be conditionally, maybe depending on the success of the previous action, which then could, in this case, in the simplified version, move the AMR just to a different position, which could be the assembly station position. And this is the same function block as before, but it has different input data. This pose 2 is the pose for the assembly station, while pose 1 is the pose for the storage rack. And this is really the concept behind the scheduling in IEC 64099 for our use case. What we also have is are different functionalities like the start and end block. We provide functionalities for stopping, pausing, and resuming the program. So, for example, after when the AMR is currently moving to the storage rack, you can press the pause button, then it will wait there, and at any time you can resume. And this is all done. This whole scheduling process using this high-level functionalities is done in IEC 64099. We then have this so-called recipe manager, which is an environment and library for EcoStruxure Automation Expert, which I said is this development environment from Schneider Electric for IEC 64099, what we are using. And there we have this template, you can say, where all these different functionalities like AMR move to other functionalities could be like pick and place actions are provided in function blocks to import. So the end user can just open this template project, use all the function blocks, drag and drop them, into the sequence, connect them in the right order he or she wants the process to be done, and therefore can create their own version of this use case, where maybe there is, after the assembly process of these parts for the fuel cell, you could add another pick and place function block to then take out the part and drive to a packaging station where the end product will be packaged for any further steps in the product chain. So as I said, this is a simplified version. I have also on the next slide this more in-depth version of our process control in IEC 64099. So the colors are still the same. Now we look from top to down because it fits better. We have here these high-level functionalities. As I said, one functionality is always one function block here in IEC 64099. We have our ROS2 interface, and we have now these different shop floor devices. So the mobile manipulator, or our mobile robot with a manipulator, is here the ROS2 device. The assembly station is a ROS2 device, so they are connected to this 64099 interface, ROS2 64099 interface. And the storage rack is not associated with ROS2. It is directly connected to the PLC using digital input-outputs, but still we can provide a single function block for one functionality. For example, this location of part, where we put in a part ID and then get back from the storage rack whether this part, where this part is located. So in the end, I will now show you a quick video of our AMR tending a machine, so you get a bit more of a vivid idea of what the whole thing actually looks like in action. And you can watch that now. So this is our mobile robot driving to this machine right now, doing the navigation and path planning. As I said, this would be done on the edge cloud, communicating via 5G. When it arrives, it checks the marker with its camera, because the navigation always has some small tolerances. Could be a few centimeters forward, backward, a few degrees in rotation offset. And there it will scan it and then calculate its exact location towards the machine. So it can now grab this part, which was loaded by the AMR, and put it into the machine. Also, all this path planning and collision avoidance with the machine is all calculated in the edge cloud. On the robot itself, it's really just controlling the motors to do what is calculated in the edge cloud. Then here is also some force control to really make sure that the part goes into this very small specific hole. And again, control is done on the edge cloud and then communicated via 5G. For these control tasks, there's really need for low latency, which can be provided by the 5G. Okay, so now we get to a quick summary of the key point we explained today in this webinar. So first, ROS2 is used a lot in robotics community and enables fast and efficient development of robotic applications. Then on the other hand, ROS2 isn't really supported in an industrial environment. So we need something like IEC 64099, which is a much more accepted standard and brings its own advantages for integration into existing factories. And we combined these two technologies to integrate this robotic application we have into an industrial automation use case. For that, we showed our mobile robotic arm, which is using edge cloud technology and communications via 5G. We developed this ROS2 IEC 640-9099 interface, and we used 640-99 to schedule the general production process. All of this together, as I said, is being implemented and tested in a real use case here at Fraunhofer IPK. So yeah, that's it for now. I want to thank you a lot for your attention and want to go over to the Q&A part. Can also take notes on our contact information here if you maybe want to message us later. And yeah, so then I would like to ask if there are any questions from the audience. I think you can raise your hand and then I can enable your microphone. Okay. So here we have Estilla Carmo from i2CAT.
Hi, good morning, everyone. Many thanks
Hello.
for the presentations. It was very interesting. I've got a question for Freya. Hope I pronounced your name okay. Because I joined the session a little bit late. It was in the middle of her presentation, and she was talking about flexible distributed architectures and all the work you have been doing in the context of the Zero Sum project. So my question, it might be a little bit difficult to answer, but it's related to how do you see what needs do you see in evolving the current state of the art? So for you, what would you say are the main research lines that should be followed over the next few years in this regard to enable these convergence of cloud computing ways of working with the needs of control architectures?
You mean my point of view towards the development of a distributed architecture of 1499 towards IT/OT convergence?
Yes, your
If
point
I'm
of
just
of mainly what research topics will need to be followed over the next few years.
Yes, definitely the research topic has to be followed because the technology is not entirely developed. We are still having so many problems to tackle. We are having, this is one of the main reasons why we participate in research projects, so that we can bring IC 64099, the flexible architecture, into the research projects. We apply, we create proof of concepts, and we get back towards our team for the feedback, how we can improve it. I cannot tell you how many years in the future I see, since I'm also working on the technology. I'm brand new. It's my third year. I have dived inside the technology and I'm trying to understand and learn every day what could be the future into IT, OT, or into the cloud computing services. So I think my answer would be I will need more 5 years to dig into a little bit deeper, and I can get you the answer from my superiors, maybe what their point of view is. Is it okay?
Yes, yeah, that's okay. Yeah, I understand. It's such a complex topic that it is very difficult even to understand all the developments that are required.
Yes, it's every day. The 1499 world is every day changing, so I cannot give you a definite answer for this question.
That's okay. Thank you very much.
Thank you.
Okay, do we have any more questions? Again, you can raise your hand and then I can enable your mic.
Sorry, another question from my side. Sorry to being.
Yeah, sure, go ahead.
Has this webinar been recorded? Is it going to be made available?
Yes, so in the beginning, I mentioned that this is going to be recorded and it will be made publicly available, most likely on YouTube.
Okay, great.
There
Thank
we
you.
have a Zero Swarm YouTube channel, and you can find it there. Okay, so if there are no more questions, we already also reached 1 hour of total time. We can wrap it up. Maybe in the end, I want to mention that you can also register on the Zero Swarm website to become part of the Zero Swarm community and get into contact with any of us via email using the contact information you see right now. And yeah, thank you again for your attention and have a very nice day.
Thank you.
Thank you.
Thank you.
Thank you very much.